Hello, my name is Darren Nattinger. I am a principal TSC at NI, and today I'm going to be presenting on runtime code analysis in LabVIEW. I'll be talking about several tools in LabVIEW that can help you troubleshoot performance issues in your LabVIEW code while it's running. Before I get started, I want to mention that this presentation is part of a series that I'm giving on troubleshooting LabVIEW applications. You can find out more information about that series by going to bit.ly/dnatlvtroubleshooting. At that link, you will find additional links for video recordings of all of the presentations that I'm giving in this series. But more importantly, you will find links to download the slides from these presentations. One of the things about these presentations is that I'm giving links to additional resources within the slides. And the easiest way for you to get those links is to download the slides and click the links from there. Now, one note before I get started on today's topic, I want to briefly cover the difference between static code analysis and runtime code analysis. Static code analysis is when you analyze LabVIEW code that is not running. And there are several static analysis tools in LabVIEW, like the VI analyzer, and even something as simple as doing a Control F to find things. You're doing those things on code that's not running. And that's going to be contrasted with runtime code analysis. So this is tools that you write or tools that you run on LabVIEW code that is running to be able to get information on things like execution time and memory usage. I have a presentation that I have given on static code analysis with the VI analyzer. The link is in the slides here. But for today, I'm going to be talking more about runtime analysis, tools that we can use on code that is running. So I just wanted to make that clarification there here at the beginning. Tools for analyzing code that's not running versus tools that for analyzing code that is running. So today, runtime code analysis, that's what we'll be talking about. And the first tool that I want to talk about for doing runtime code analysis for troubleshooting LabVIEW applications is the VI profiler, which is the easiest way to identify issues with execution time in your LabVIEW code. Now, I call it the VI profiler. That's a colloquial name that a lot of longtime LabVIEW programmers use for this tool. It's actually called the Profile Performance and Memory tool. That's the official name for the profiler, and you launch it from the Tools menu. So whenever I use the term VI profiler, I'm referring to the Profile Performance and Memory tool. Now, I mentioned that this is the easiest tool for doing runtime code analysis, and it totally is. If you look at the slide here, I kind of give instructions on how to use the profiler. The first thing you want to do is check the timing statistics checkbox, because that's going to give you some really useful information to find out number of runs. Whenever you're benchmarking some LabVIEW code, it's very easy to fall into the trap of spending too much time looking at the wrong parts of your code. And what I mean by that is you may identify a VI that's doing some sort of large array manipulation or string manipulation, and you may spend a lot of time trying to eke performance out of that VI only to find out that that VI only runs once. And you've got VIs that are running inside of a loop thousands or millions of times, and those are what's causing the performance issue, but you were focusing your efforts on the wrong place. By using some of the additional information in the profiler, like the number of runs column, that's a very quick way to identify, oh, these are sub-VIs that are running a whole bunch of times, so maybe I should focus my effort on those. But as far as using the profiler, it can't get any simpler than this. You click the start button, you run your code, you click the snapshot button, and then you start looking at the results to try to figure stuff out. Some people I know have been intimidated by trying to run tools to benchmark code. The profiler should not intimidate you. It is an extremely easy tool for benchmarking code. Now, I've got one trick that I use, because the thing about the profiler, despite the fact that, as I mentioned, it's easy to use, there can be some problems that you might have identifying. Like you might get the performance issue narrowed down to an individual VI, but once you're there, you may have a little trouble figuring out where to go next. And so I have this trick that I do, and it's described here on the slide, where you identify parts of the diagram that you may think have a performance issue, and you just highlight those parts of the diagram and do edit create sub-VI. Now you've got an untitled sub-VI that's sitting there. You don't have to save it. You don't have to make it part of your code base. It is just there as a temporary tool to give you another VI that'll show up in the profiler. Now So now you can take a block diagram and let's say make a sub-VI here, a sub-VI here, and a sub-VI here. And now those three sub-VIs are going to show up in the profiler. So whereas that VI may have taken 1 second to run, well, now you've got a sub-VI that takes half a second, and two sub-VIs that both take a quarter second. So now you can narrow down further which parts of that diagram are taking more time to execute. Now, I have given a presentation on speeding up execution time before. You can get it at bit.ly/slowvis. And in that presentation, I talk about I go into a lot more detail about the profiler than what I've described right here. I also have another presentation called Brainless LabVIEW where I talk about benchmarking techniques for code, and you can take a look at that as well. I'm not going to cover things like how the compiler works in this presentation today, but there's a lot of useful information on that available on the web, and you can Google the terms that are on the slide to find some articles that are written about how the LabVIEW compiler works under the hood. But I just wanted to mention here, there's a lot of resources for learning about this tool and a lot of other topics related to performance. But now I'm going to go ahead and switch over to a demo to show you the profiler in action. So this demo comes from a real world use case where a team at NI contacted me and told me this was the DACMX team. They had written some tests for DACMX and how it was logging data to TDMS files. And they had this big folder of very large TDMS files. And what they wanted to do is they wanted to take that TDMS data and take a look at it in Microsoft Excel so that they could run some analysis on that data. So they wrote this tool that takes all those TDMS files and converts them to comma-separated value files, CSV files, in which they could then load in Excel and do stuff. But the problem was that this tool was taking a very, very long time to run. And so the DACMX team came to me and said, hey, can you help us figure out why our tool is taking so long to run and help us identify ways to make it faster? So I said, sure. So I've got sort of a sample of what their code was like. In this case, the VI takes 0.8 of a second to run. This is just running on a single small TDMS file. So imagine that this VI is running on a huge folder of large files and it takes a really long time to run. So I did I sort of inspected their code, did an analysis of their code with the profiler, and came up with several ways to speed up their code. And with my improvements, it got over twice as fast as it was executing previously. So what did I do? How did I speed up their code? Well, first of all, I took a look at what they had. So this is the code that would take in, imagine that this array of waveforms is coming in from a TDMS file. And what they're doing is they're creating the CSV, and then they're manipulating or sort of pulling out the interesting data from the waveforms in these for loops here, and then writing that to a file, the text file on disk. So the first thing I did was what I suggested in the slides. I ran the profiler on this application. So I'm going to go to Tools, Profile, Performance, and Memory. And remember, the first thing you do is check timing statistics because you want to get the number of runs, which is an interesting statistic. And then I just click Start. I click Start in the profiler. I run the VI is done. And then I come and I do a snapshot. Unfortunately, this is not at all helpful because I'm seeing that this VI is taking 800 milliseconds to run, which I already knew. There's no other useful information here. So let's move on to that tip that I described in the slide where we make temporary sub-VIs to narrow down what parts of this diagram are taking a long time. So it actually looks like there's pretty easy sort of, I guess, dividing points on this diagram of things that I could benchmark. I could take this for loop here and see how long that takes to run. I could take this for loop here and see how long that takes to run. And when I first saw this code, I thought, well, I think it's probably the most of the time is just the writing to disk. So why don't we make a sub-VI that just wraps the write to text file function and see if that's taking a long time. So now I've taken my code, I've made these temporary sub-VIs. I'm going to restart my profiling. I'm going to run the VI, and then I'm going to do another snapshot. Now we've got some more interesting information. We've got these 3 sub-VIs that are now showing up. So I'm going to bring up my context help window, and I'm going to hover over what was my first suspect, which was the file IO, the write to text file. Well, I see that that's untitled 5, and as we can see here, untitled 5 takes up very little of the total amount of time to execute. 10 milliseconds. So my hunch was off. Now I look at what else there is. Untitled 4, we can see also takes a very small amount of time. It looks like the majority of the execution time being taken up is with Untitled 3 here. So the code that I wrapped in this for loop. So now that I've done that identification, I can actually just press undo 3 times in my main VI and get back to where I was before without the sub VIs. So you can see that that trick of creating temporary sub VIs is extremely handy for benchmarking, and then it's very easy to get back to where you were just by undoing those creation of sub VIs. So it looks like the code inside of this for loop right here is the most suspect. Now, I'm not going to go into a lot of details about what I did to sort of narrow down what the problem was in this code. What I'm going to do instead is just show the diagram of the faster VI. So here's the VI with my improvements. So what I did was I sort of identified which things could, which parts of these changes contributed the most to speeding up the VI. Well, 80% of the speed improvement came from consolidating these 2 loops, because you can see we're just building up an array of strings and then immediately iterating on it in this next loop. All of that could be done in a single loop without having to create a new loop. I also started using parallelization. So parallel for loops are another great way to speed up code execution. And then I also used inlining. I talk about inlining a lot more in that speeding up VIs presentation that I referred to earlier, which I will also have a link to later in the slides in my summary. So, but consolidating loops, parallelization, inlining, and then also the code that generates the timestamp inside of this VI. Now here is kind of an aside that I'm going to mention. Prior to working as a TSC at NI, I was in LabVIEW R&D. And when the DACMX team came to me with this issue and I identified all of these ways to improve performance, I also discovered that this VI, LibVI right here, this is one of the VIs that's part of the waveform API. That is one of the areas where I found a way to speed up the execution. And so not only did I fix that in the code for the DACMX team, but that change also went into core LabVIEW. And this VI is now faster in future LabVIEW versions than it was before, based on my ability to benchmark this and improve the speed. So when you work on benchmarks and you are using these tools that I described in this presentation, troubleshooting ways to speed things up, and you identify parts of LabVIEW itself that could be improved, please share those with NI through the TSC group or however, because we can incorporate those changes into VI LibVIs to improve performance for all LabVIEW users if you happen to find some of these issues while you're working on code. All right, so I'm going to go back over to the slides now. And I'm going to talk about the next tool, which is profile buffer allocations. Now, you may have heard of a tool called show buffer allocations, and I'm going to refer to that later in the presentation, but that's not what I'm talking about right now. I am talking about the profile buffer allocations tool that allows you to identify specific terminals on the block diagram that are allocating large memory buffers. This is what the profile buffer allocations tool looks like. So one of the things that we have to troubleshoot sometimes when working on LabVIEW applications is memory usage. We may find that a LabVIEW application is causing the computer to run out of memory or to run low on memory. We may find that memory usage is creeping up as our program runs. And the profile buffer allocations tool is one of the easiest ways to identify places where large memory allocations are taking place. So I'm going to switch over to a demo now to illustrate how to use the profile buffer allocations tool. So here we have a sample VI. I'm going to just run it, and you can see that it's doing some sort of puzzle solving. I don't even remember what this is doing specifically. It kind of looks like Tetris almost, but this is a VI that was written to do some sort of solving of an algorithm. And it has been identified that this VI is using up too much memory while it runs. So what we're going to do is we're going to use the profile buffer allocations tool to find places in this code where too much memory is being allocated. So once again, I'm going to go to the profile menu and launch the profile buffer allocations tool. Now, by default, this tool will look for allocations that are over 20 kilobytes. For the purposes of this demo, I'm going to make it the lowest possible threshold, which is 1 kilobyte. So once again, similar to the profiler that I showed before, what we're going to do is we're going to click Start and run our VI. And once our VI is done, we're going to click Stop. And now the profile buffer allocations tool has identified all the places where memory allocations have taken place that are greater than 1 kilobyte. And you can see that there are several. But here's another place where the number of runs is going to be a useful metric to help us understand places in our code where large memory is being allocated on a frequent basis. Now, in this case, this is a small demo with small allocations. You may have an application where there's a VI that runs one time, but you find through using this tool that it allocates a gigabyte of memory. So that's a case where a number of runs really isn't something you're paying attention to. You're paying attention to the absolute very large amount of memory being allocated. But in this case, let's take a look at some of these places that are being called a whole lot of times. We can see here's a VI being called over 7,000 times. It's doing an allocation. So one of the great things about profile buffer allocations is how granular the results can be for us. Remember I showed the profile earlier whenever I was benchmarking the code, the execution time? The VI profiler can also give you memory allocation information. So it can tell you, in addition to, this VI took 100 milliseconds to run, it can also tell you, it also, allocated 50 kilobytes of memory or something. But the reason I don't suggest using the VI profiler for memory type things that you're troubleshooting is because it can only get you information to the VI level. The profile buffer allocations tool, the one that I'm showing right now, can get you allocation information down to the terminal level within a VI. So much more granular and much easier to identify those memory allocation issues. So what I'm going to do is I'm going to double click on this result. And you can see that it brought up this diagram and highlighted a single terminal. So that output terminal on the for loop is causing the memory allocation that it was identified by the profile buffer allocations tool. So now this gives me a specific place to look on my diagram. I can see that it looks like this code is taking an array of Booleans, and it's not even using the values. It's just running 2 for loops to build up a new array that's the same size as the previous one, but full of false values. We could probably replace this code with an initialize array function. I don't know if that would help with the memory issue, but it's certainly going to be cleaner and more readable code. So that's one area we can identify. And I'm also looking at this code over here and seeing that we're doing some Boolean logic on this array of only false values that we've generated. It looks like we're just replacing pieces of it with things that might have trues in it. But for the rest of this, we're going to be performing Boolean operations on an array that contained only falses. So this looks like another place where maybe we could sort of consolidate some of this code here into some much more efficient code without having to iterate over everything. So, I'm not going to try to figure it out right now during the presentation, but I'm saying the profile buffer allocations tool took us down to a single terminal that we can now sort of center our efforts on how can we make this code allocate less memory. All right, so I mentioned that I just demoed the profile buffer allocations tool. Well, there's another tool that ships with LabVIEW called the show buffer allocations tool. And I don't know who named those tools. It was not me, but it's kind of confusing. They've got almost the same name, but they do different things. The show buffer allocations tool is used for a game. I guess we could call it a game. Maybe it's not a game when you're in the middle of it, called hide the dots. If you've ever heard anyone at NI or any old-time LabVIEW programmers refer to hide the dots, they are referring to using the show buffer allocations tool. And this is a way to identify places on the block diagram where LabVIEW may decide to allocate memory. Now, that is an extremely important use of the word may, because a lot of people see hide the dots and they think every single place that I see a dot is a memory allocation, and that is not true. That is a buffer allocation. That is a place where LabVIEW is indicating to you, the LabVIEW programmer, hey, this spot, when this code runs, I may decide to allocate memory at this spot. It doesn't mean that LabVIEW is absolutely going to do that. So playing hide the dots is not always going to solve your memory issues that you're troubleshooting, because it may turn out that even though there's a dot there, when the code executes, there's not an allocation at that place. There's an allocation somewhere else that's causing the issue. So I don't really advocate the use of the show buffer allocations tool simply because profile buffer allocations is so much more useful. Nevertheless, I wanted to mention it here in the slides just so you would know it's there. Now, one way to sort of take care of buffer allocations is using the in-place element structure. If you have not incorporated the in-place element structure in your regular LabVIEW programming, you definitely should. Take a look at this code here. We have code on the left that is indexing out from an array and then replacing array elements. The code on the right does exactly the same thing, but it uses the in-place element structure to do so. And in doing this, it can more efficiently choose to not allocate buffers because you are telling LabVIEW that you want to operate on those values in place. Now, I'm not going to get into details today about what in placeness is. It is LabVIEW's ability to reuse data buffers that it has allocated for previous operations. And by using the in-place element structure, you can explicitly tell LabVIEW that you know you're happy to reuse different things that have been allocated, because in this case, you can see in this diagram, we are replacing elements in an array. We're not adding new elements to the array. We're not deleting elements from the array. We've got an array. It's already got all the values that we need. We just need to change the values of a couple of things that are already in there. By writing the code on the right, you're telling LabVIEW, I will not be adding or removing things from this array. I'm just changing values. And that means LabVIEW doesn't have to allocate or doesn't have to figure out if it has to allocate any new memory. So just wanted to throw in a good plug for the in-place element structure. If you have not incorporated its use, it's one of the easier ways, honestly, to improve memory usage issues in your LabVIEW code, and maybe something less stuff that you have to troubleshoot. In my slow VIs presentation that I talked about before, I have had to debug applications where code was written and looks more like the code on the left. And by changing it over to be the code on the right, it actually resulted in significant memory and performance improvements in the code. All right, so now I'm going to talk about the desktop execution trace toolkit. If we have a spectrum of easy profile tools and more complex functional profile tools, the VI profiler is going to be on this end, and the execution trace toolkit is going to be on the opposite end. This is a tool that provides comprehensive runtime performance information. If you want to know every single detail about what happens when your code executes, this is the tool you use. However, in saying that, it hopefully is obvious that there's a lot more of a learning curve for using the desktop execution trace toolkit than there is for using the profiler. Nevertheless, it is such an important profiling tool for a lot of applications. I do want to cover it here in these slides. So one of the things about the desktop execution trace toolkit is that it lets you figure out what type of events you're interested in seeing. So there's a lot of filtering settings. If you are interested in identifying reference leaks, you can just take a look at those. If you are only interested in looking at memory allocations, you can just take a look at those. If there's some sort of race condition in your code involving like when some queues and notifiers are used and when some VI execution events happen, you can just filter on those types of events as well. The way that the trace toolkit works is you can see certain types of events show up in the trace as different colors. You can see that we've got the queue events showing up in light and darker blue in the list, and you can see reference leaks showing up in yellow. So just visually, you can scan the trace. The trace is going to be huge. You're about to see that in my demo. But if you are looking at everything, then at least there are ways to sort of key into certain types of things that show up in the list. And then another thing that the trace toolkit can return to you is if functions like built-in LabVIEW functions return errors, you can see those show up in the trace as well. And finally, if you as the LabVIEW programmer have something that you want to show up in the trace tool, the trace, but is not one of those predefined things. It doesn't have to do with queues or notifiers or VI execution or whatever. It's something that you want to say, hey, I want something to show up in the list at this point in the code. Then there's also, you can actually drop a function on your block diagram called generate user-defined trace event that will, you wire a string to it, and then that string shows up in the desktop trace toolkit when it actually gets to that part of the code. Now I'm going to switch over to a demo and kind of demonstrate all of those things that I just talked about. So one of the things you have to do is when you're using the trace tool, you have to make sure that VI server is enabled in LabVIEW. So the first thing we're going to do is make sure that's the case. I'm going to go to Tools, Options, and under VI server, we need to make sure that VI server is turned on. we give it just a moment here, we can see that it is the TCP access to VI servers turned on, and we need to remember this port value. In my case, it's 3372. So I need to just keep that in mind, 3372. Now I'm going to go ahead and launch the desktop trace toolkit. And one of the first things that we're going to have to do in the trace toolkit is specify which port we are using. So we can see up here at the top, it says a different port. It says 3363. That's not what we want. We want 3372. I'm going to quick refresh. And now we can see my project shows up in the list. So I've got this project right here, Actor Framework Demo. This is the project that I want to do a trace on. So what I'm going to do is I'm going to click Start in the Trace tool. And I'm going to open up Splash Screen, and I'm going to run it. Now, right away, you see a ton of things showing up in the list. I'm going to click a few buttons in the demo and stop, and then I'm going to stop my trace. Now, take a look at that. I ran a VI, clicked 3 buttons, and the VI stopped, and 240 events were traced in that short period of time. That's what I was mentioning before when I said the execution trace toolkit is an extremely comprehensive tool because it is going to provide every piece of information that you might need. If we scroll up through the list, we can see things like VI calls, VI returns, event structure, events taking place, notifier events taking place. But we also see a reference leak. So a reference leak sounds like a pretty big deal, right? Well, let's double click on that reference leak. And what it's going to do is it's going to open the diagram that caused that event to fire. And if we look at the diagram, we see that there's this open VI reference function. We can see that the reference is going into a shift register. And we can see that that reference is never being closed. So this is an accurate sort of, I guess, return value from the trace toolkit that we had a reference leak. However, if we look at this diagram, we see this comment here. We deliberately leak the open VI reference and then a whole bunch of other stuff. So that's being done on purpose. Nevertheless, the trace tool was able to provide us that information so that we could at least see, is this something that I need to be concerned about? Well, apparently not, because whoever wrote this VI told us that it's being done on purpose and for performance reasons. All right, so this particular application that we're looking at right now is an Actor Framework application. And it turns out that Actor Framework applications, very often there are issues that someone needs to troubleshoot. A lot of the times they're based on VIs that were supposed to stop but never did, or VIs that get launched in a different order than you think there are. The thing about Actor Framework is that it spawns reentrant instances of VIs. And anytime you have a framework like that, it can sometimes be difficult to debug when things aren't acting like they should, or when VIs aren't going out of memory when you think that they should be. Well, thankfully, the Actor Framework itself has some built-in debugging behavior that can hook into the desktop execution trace toolkit. And it is very easy to enable that functionality. So what I'm going to do is I'm going to go into the project properties. So I'm going to right click on my project and say properties. And we can see under conditional disable symbols, there is one called AF debug trace. I'm going to change that from false to true. Now I'm going to create a new trace. I'm going to switch over to the Actor Framework project, and I'm going to click Start. Now I'm going to do exactly the same thing that I did before. Click Start, run the VI, click the buttons, 1, 2, 3. And then I'm going to click Stop in the trace toolkit. Now, if we scroll through the list, we can see that there are several events from this library called afdebug.lvlib. Those events were not in the previous trace. And to prove that, if I go to View, I can select Compare Traces. Now I can compare the two traces that we just did. And we can see that if we scroll through, there's all these AF debug events that took place when we ran the second time than from when we ran the first time. So the Actor Framework debug can give you all sorts of information, like when actors were added to and removed from the actor registry, and things like user-defined events that tell you things like this actor has registered a message to this particular actor. So these are all details that you will not get just out of the box. You need to go change that debug symbol. Now, this is a debug symbol that you can add yourself. The actor framework project template includes this symbol. That's not something that has to be included. If you've got an actor framework project, you can manually type that symbol name in, AF debug trace, with a value of true, to start seeing those actor framework debug library messages showing up in the trace. Now, one other thing I want to show is the filtering that I talked about before. So let's say we were working on an application and there were some reference leaks that we were concerned about. So if I go into view and pick filter settings, remember, there's hundreds of events that have shown up in this trace. I'm going to select just the reference leaks and click OK. And now you can see we went down from hundreds to 3. There are 3 reference leaks in this code. And again, if we double click on any one, we'll see that same code with the message about deliberately leaking the reference. So this was just a very quick introduction to the desktop trace toolkit. There's a lot more that could be said about it, but I just wanted to kind of illustrate this is kind of the other end of the spectrum. Every possible piece of information about when VIs execute and when VIs spawn and when queues fire and event structures and all that kind of stuff, you can get that granular information by using the desktop execution trace toolkit. One other tool I wanted to mention in this presentation is the LabVIEW Task Manager. This is not a tool that ships with LabVIEW. This is a tool that you have to download from lavag.org. I've got the link down at the bottom of the page. And the LabVIEW Task Manager is designed sort of in the same spirit as the Windows Task Manager. So this is a tool that will kind of show you all of the information about the VIs that are currently executing. You can see in the screenshot here what I'm talking about. This is an excellent tool for debugging issues related to reentrant VIs. I mentioned before that sometimes with an actor framework type application, you may run into issues you have to troubleshoot where actors got spawned, but they never stopped. That's not something that's specific to the actor framework. Any application that spawns reentrant clones, the DQMH that I mentioned in my previous presentation, that's an example of one. Pretty much any framework that facilitates dynamic launching of VIs is going to be doing it with reentrant VIs. And the LabVIEW Task Manager provides some mechanisms to sort of identify some VIs that are still in memory and running, but they never stopped and nobody is able to stop them now. Now, one thing that I will say, I have used the LabVIEW Task Manager for debugging and troubleshooting applications before. If you've got a very large LabVIEW application with thousands of VIs, with just a whole lot of things being spawned in parallel in reentrant instances, I have seen this tool get bogged down. I have seen it get non-responsive. It gets to the point where I can't use it to troubleshoot the application that I'm working on. So that's something to keep an eye out for. It's not a perfect tool, but it is a great tool. It's better than nothing. But keep an eye out for that it can get bogged down with those large applications. Okay, so to summarize what I talked about here today, if you are needing to troubleshoot execution time issues, VIs that just run too slow, don't be intimidated by the VI profiler. It is extremely easy to use, especially when you take into account tricks like creating temporary sub-VIs to narrow down execution time issues. Don't be afraid to use the VI profiler. Now, for benchmarking issues with memory, so now you're not troubleshooting execution time, but you're troubleshooting memory usage. The profile buffer allocations tool is a great tool for that. Prior to this tool, we had the show buffer allocations tool, which let us play hide the dots, but that is nowhere near as useful as the profile buffer allocations tool to be able to identify those specific terminals that actually did allocate large amounts of memory while the code was executing. Now, in terms of the most comprehensive runtime debugging tool, that's definitely the desktop execution trace toolkit. It provides all the functionality you would need, every single little nitpicky detail of what happens when your VI executes. But at the same time, it is a harder tool to learn and a harder tool to use. And now you've got this immense stack of trace data that you can filter, but it still takes a while to figure out to narrow down where the issues are happening. but it is the most comprehensive tool for the job. And then I quickly mentioned the LabVIEW Task Manager, another tool, a third-party tool that you have to download from LabVIEW that can help debug and troubleshoot issues pertaining to execution time, particularly reentrant clones. So I have several items of homework for you for this presentation. The first is to make sure that you get the slides from bit.ly/dnatlv troubleshooting. And that's where you're going to be able to gain access to this video recording, these slides that have all the links, and the demo VIs that I used in this presentation, and all my other LabVIEW troubleshooting presentations as well. If you haven't already, you should watch my presentation called Quick Drop Your VI Execution Time. In that presentation, I spend the entire time talking about the VI profiler. So here I only spent a few minutes on it, but I go into much more in-depth discussion of using the VI profiler, some more tricks of the trade for using it, and more demos of real-world code that I was able to speed up purely by using the VI profiler. I also have my presentation on improving your LabVIEW code with the VI analyzer. Now remember, this presentation was on runtime code analysis. Static code analysis is a whole nother world with a whole different set of tools. And my VI analyzer presentation is a great introduction for that stuff if you haven't seen it already. And finally, I only briefly mentioned benchmarking code in this presentation. In fact, I didn't really talk about it. It just kind of happened on some of those demos. I've got a presentation I've given called Brainless LabVIEW, where I talk about a lot of different topics of things pertaining to best practices in LabVIEW and maybe rethinking some of those. And one of the things I cover in that presentation is benchmarking techniques. So a lot more detail on benchmarking than what I talked about today. And with that, thank you very much for watching this presentation. Good luck with troubleshooting runtime issues in your LabVIEW code. Thank you.